Welcome back to linear algebra. Today we'll talk about the spanning set theorem. So what does the spanning set theorem say? Well, it says if S equal to vectors v1 through vp is a set in V, and our h is equal to the span of our vectors v1 through vp, then if a vector vk in our set is a linear combination of the remaining vectors, then we say that S minus that vector vk still spans h. So the span of v1 through vp minus vk is equal to the span of v1 through vp with vk. And our second condition says that, look, if h is not just the zero vector, then there is some subset of h that is a basis. So we will have a basis in there. So let's prove this. Okay, S minus vk still spans h. So again, S is equal to v1 through vp. Let's take an arbitrary vector x. And this arbitrary vector x is going to be a linear combination of c1 v1 all the way up to cp vp. So this vector x is in our span. It's arbitrary though. So we're going to pick a vk that is a linear combination of the other ones. For notation terms, we're going to pick that vk and we're going to make vk be the last vector in our set. So we're going to call it vp. So vp is going to be a linear combination of all the other vectors. So this will be a1 times v1 all the way up to a p minus 1 times vp minus 1. So vp is a linear combination of the rest. What we can do now is we can substitute this in for our representation of the vector x. So now we're going to have x is equal to c1 v1 all the way up to cp, but when this vp goes in here, we're going to replace this with a1 v1 all the way up to a p minus 1 vp minus 1. So now our vector x is a representation of just the vectors v1 through vp minus 1. But x was arbitrary, so that means that we can do this for any vector x. So this means that the span is still the same. So because I took an arbitrary vector, and I can rewrite that vector as a combination of v1 through vp minus 1, that means that the span is still the same. So that's the proof of part 1. The second part says that if h is not the zero vector, then there's a subset that's a basis. Okay, so there's two conditions. One, we could have that S is linearly independent. So if S is linearly independent, then we're done, because it's a basis. Okay, the second condition, which is more important, is what if S is linearly dependent? So what happens if it's independent, or if it is dependent? Okay, if it is dependent, then we can rewrite one of the vectors as a linear combination of the others. So we're just going to take S and we're going to remove that vector vk. And now there's two conditions. One, if it's now linearly independent, we're done. So that's good. Two, once we remove the vector, if it's still linearly dependent, then what we do is we just repeat the process, and we keep going until it becomes linearly independent. Now we know that this zero vector cannot be a basis. So what will happen is we'll keep reducing and we'll never quite hit 0, but we will eventually find a basis for h. So if the spanning set reduces to one vector, it is not going to be the zero vector, because it is going to be linearly independent, because we're just reducing the linearly dependent set until we get something that's linearly independent. So essentially, we're removing all of these redundant vectors. Okay, so that's the spanning set theorem. So we have v1, v2, and v3. These are three vectors, and we have h as the span of these. And we know that if we take 4v1, add 5v2, and subtract 3v3, we're going to get the zero vector. I'm asking you to find three distinct bases for h. So we're going to have a basis 1, we're going to have a basis 2, and we're going to have a basis 3. So how do we do this? Well, we know that we can rewrite one of these vectors as a linear combination of the other. So what this means is we can pick any one of these vectors and we can remove it. So one of our bases could be the set containing v1 and v2, because we just removed vectors number 3. v2, so a second basis, we can remove vector 2 instead, so we're left with v1 and v3. For our third basis, we could remove v1, so we're going to be left with v2 and v3. So these are 3 distinct bases for h, or bases for h. Doesn't even matter what these are. We just have to make sure that these 2 are also not linearly dependent. I'm going to save the calculations because it would take a bit of time, but these are not linearly dependent. These are in fact linearly independent sets that span the space that we're looking for. So this is good. These 3 are good. Okay, next question. We have 3 vectors, v1, v2, and v3. We have 1, 0, 1, 0, 1, 1, and 0, 1, 0. And h is going to equal the set of vectors that are of the form ABB. So essentially, the first entry is a number, doesn't matter what it is, but the second and third entries are always going to be equal to each other. So we can rewrite this vector ABB as a linear combination of v1, v2, and v3. So we can take a times 1, 0, 0, plus b minus a times 0, 1, 1, plus a times 0, 1, 0. So we can prove these are equal. This is just a0, 0 plus 0, b minus a, and then we add together 0, a, 0. Okay, so when we add the 3 together, this should be equal to a, b, b. Okay, that looks good. It does not look good because one of these entries was written wrong. Okay, so that should be a 1 there, which means this should be an A. Now it is good. Okay, problem fixed. Okay, so is v1, v2, and v3 a basis for h? Well, what this means is that our v1, v2, and v3, so these are linearly independent, and we can't write these as a linear combination of each other, so that's good. But there's one key point. These vectors, they have to be in h. So these have to be an element of h. What's the problem? Well, this v3, 0, 1, 0, is not in h. Because this is not of the form ABB. The second and third entries are different. Therefore, this cannot be a basis for h, because v3 isn't even in h. So, of course, you can't have a basis for something if you take a vector from the basis, or we take a vector from the space. We have to have it from the space. v3 is not in the space, so where are we pulling v3 from? Well, we can pull it out of our butts, but that's not good mathematically, so don't do that. It also might hurt a bit, so not a basis. Alright, that's the spanning set theorem lecture. If you have any questions, please leave them in the comments below, and I'll answer them the best that I can.